start with part 1A, we're looking for the speed once it makes a 25 degrees compared to when it's initially horizontal to here. So then what we know is this is going to be a change in y, which is in this case is L sine of 25. That'll be used later. So now what we can set up is MEI is equal to MEF, because we know that mechanical energy in this scenario is conserved, and we're only going to look at the as from the top to this point right here. So we're just going to set up the PE, the work done by the force of gravity. So it will be Fg times change in y, and then all that will be converted into Ke. So then Fg, in this case Mg, as Emily declared earlier, our change in y is L sine 25. And then Kef will be just 1/2 m of the, in this case, this will be big M. And so will this also be big M, because then that represents the ball. And then it will be Vs squared. We cancel out these m's right here because they're the same one. And we can multiply both sides by 2 to isolate for Vs squared. So now we're left with 2gl sine 25 is equal to Vs squared. If we square root both sides, then we're left with 2g L sine 25 is equal to Vf. And once you simplify that, you should get 4.984 meters per second, which will be the speed once it makes a 25-degree angle. We're trying to find our A net. So first we're going to find our AC, which is just the V squared over R. In this case, this V is the V we found in the previous one, which is just going to be 4.984. And we're going to square that every divided by the length of the pendulum, which is 3. After that, our AC should be 8.283 meters per second squared in magnitude. And our A tan, next we're going to find our A tan. So if we look here, we're going to draw, this is the FG, and we're going to draw its components. So FGX is right here, and it's FGY. Now this is a 90-degree angle, and it's similar to this one, but for this we're going to have to rotate it. Actually, we're going to have to flip it. So then that means this here will be our 25-degree angle, and then this here will be the complementary angle to this, but we're only caring about this one for now. So if that's the case, that means this here, that means FGX is going to be FG cos 25. But since we're just looking at the acceleration, it's just going to be G cos 25. So now our A tan is going to be just G cos 25, and that is approximately 8.881 meters a second squared. A net. Now we're going to try to find A net and acceleration vector, so we have to use Pythagorean theorem. So it's A net squared plus AC squared plus A tan squared will equal to A net squared. I'm going to simplify A net by square rooting both sides. So now you have A net is equal to square root of AC squared plus A tan squared. But I'm going to plug it in. So AC was 8.283 squared, and A tan was 8.881 squared. And once you simplify that, your A net will come out to 12.145 meters a second squared in magnitude. Okay, so for part C, angular acceleration, so the magnitude of that, so we know alpha is equal to just A over R, but in this case, we're going to look at A tan, so then it's just alpha is equal to A tan, which is for G, which was 8.881 over R, which is the length of the string of the pendulum, which was 3, and then after that you just get once you simplify that, if we 1 over 3, you just get 2.96 rads per second squared. That's just angular acceleration. Okay, so for 1D, we're trying to find the tension. So we're going to set up net force. Net force at that point is equal to Fc. And what we know is that because of this, tension is going to point up, but then gravity is going to point down. So we see, right, T minus Fg is equal to Fc. And then we can isolate for T by writing T equals Fc plus Fg. Now for Fc, what we're going to need to find is V. So we're going to set up our other, we're going to set a mechanical energy. MEI is equal to MEF. So if we're taking it from the top here to here, we're going to use this as the reference point. So from here to here, so we're going to set up PE gravity, or work due to gravity. So it would be Fg times the change in Y is equal to 1/2 m, big M in this case, times Vf squared. This Vf here represents the speed at the bottom right before it hits the block. So now we could explain this. So it will be mg, and then changing Y here, since it's going from perfectly horizontal to perfectly vertical, it would just be times 3, and now be equal to just 1/2 times big M Vf squared. And then you can cancel out the m here and multiply by 2 on both sides. So you get 2 times 3g equal to Vf squared. And you can square root both sides. And then once you do that, your velocity at that bottom should be about 7.668 meters per second. And this would be your speed at the bottom. My bad, not the velocity. This is the speed, or magnitude of velocity. And so now we can plug it back into here. So we know it's T is equal to, so Fc in this case is M, big M, because that's the bob, that's the pendulum, times Vf squared over L, because in this case R is going to just be L, our radius, plus the mass of the bob times G. And then you just start plugging in. So T, so we know our mass of the pendulum is 1.8 kilograms times 7.668 squared all over 3, plus our mg, so it's 1.8 times 9.8, and then you should get, once you simplify that, you get approximately 52.92 newtons as the tension, as the magnitude of the tension at the bottom right before it collides with the block. To start off 1E, so we're trying to find the velocity after collision, and what we know is that before the pendulum hits the block, what we found in the previous problem, so it's Vf. So in this case we're going to as Vi, V1I, which is going to be the pendulum's initial speed before it, velocity before it hits the block, which was plus 7.668 meters per second. And then now we're adding this set of momentum. So Pi is equal to Pf because the momentum is conserved. And what we know is that in this case it would be M1 V1I, which is the momentum of the ball before it hits the block. And then we also know it's M2 V2I, which is 0 because then the block doesn't move. It's equal to M1 V1F, which is the final momentum, plus M2 V2F, which is final momentum of the block. This one's for the ball. And we're trying to isolate for V2F, so we could cancel, because then we're trying to find V1F, so we need to get rid of this variable we don't know. So I'm going to isolate for it, so it's M1 V1I minus M1 V1F is equal to M2 V2F. And you just divide both sides by M2, and after that you get M1 V1I minus M1 V1F all over M2, and that'll be how you you find V2F. So after we found our our V2F, we're going to set up KE. So since this is elastic collision, KE is going to be conserved. So we can say KEI is equal to KEF. Now we can set up, so we first have the KE of the pendulum before, so it's 1/2 M1 V1F squared, or 1I squared, my bad. Now on the other side, we have 1/2 M1 V1F squared, and this is going to be the final KE of the pendulum after collision. And we're going to add the KE of the other one of the block, which is 1/2 M2 V2F squared, and that's the KE of the block. And for the initial KE of the block, it's 0 because it's initially at rest. So now we can start playing into V2F, so we could rewrite the equation. So it's 1/2 M1 V1I squared, so it's 1/2 M1 V1F squared. And we're going to add M1/2 M2. Well, in this case, we would cancel the 1/2 because it'll be easier to manage without having to worry about 1/2. Now, our V2F, what we saw earlier, was M1 V1I minus M1 V1F all over M2, and this whole thing is squared. And now what we can do is we can expand this. So let's rewrite the equation. M1 V1I squared is equal to M1 V1F squared plus M2 times, I'm going to factor out M1 and M2 per separate, so it's M1 squared over M2 squared. And now this is going to multiply this V1I minus V1F squared, so you could just FOIL it. So in this case, it will be V1I squared minus 2V1I V1F plus V1F squared. And after this, I'm going to move this M1 V1I squared to the right, so later I can solve for V1F. So we put 0 is equal to, what we know is negative M1 V1I squared plus M1 V1F squared plus, this is so it's M1 squared, and this is M2 over M2 squared, which is M2, so it's M1 squared over M2 multiplied by, and then we're going to distribute to each term, so it's V1I squared minus M1 squared over M2 times negative 2 V1I V1F, and this is going to be plus M1 squared over M2 times V1F squared. So now before we move on, well, we have to first correct this mistake right here, which should be a plus, not a minus. That's the minus rate countable right here. And now the next step is to combine like terms. So here we have a negative M1 V1I squared, and you have an M1 squared over M2, so we combine them. And since they both have V1I squared, I'm going to factor it out, so V1I squared times, put M1 squared over M2 minus M1, and then we look at I'm going to combine the V1F squared, so there's M1 V1F squared, and here's M1 squared over M2 V1F squared, so it's plus V1F squared times M1 squared over M2 plus M1, and here we just have M1 over M2, and this is the last term, so it's just negative 2 V1I V1F M1 squared all over M2. And now we can start plugging in numbers. So we're going to set up 0 is equal to, and we know here, we're going to put up here space, 0 is equal to V1I squared, which is 7.668 squared, times M1 squared, which we know is 1.8 squared over M2 is 0.4 minus 1.8 because that's M1 plus V1F squared. We don't know what V1F is, we're trying to find it, times M1 squared over M2, or which is just, in this case, 1.8 over 0.4 plus 1.8 and then minus this one 2 times 7.668 times 1.8 squared v1f over here, all over 0.4, which is going to be our m2. And then what you can do is you can simplify this into, so this becomes 370.44 plus 9.9 v1f squared minus 124.22 v1f. And what we notice here is that this is in the form of a quadratic, because we have a variable, our singular variable v1f, and it's squared. This is just v1f times a coefficient, and it's just a constant. So what we could do next is we're gonna go to our calculator, or use quadratic, but in this case we're gonna use calculator. And so once you plug in all the numbers correctly, 9.9, 424, 370.4, you get two values. So you have 4.8797 and then 7.668. So, and the correct one will be the x1 here, 4.879, because the 7.668 is the initial velocity of the pendulum right before it hits the block. So there's no way it could be this, because that means its velocity is conserved. I mean, it's and then for some reason, and somehow momentum is not conserved. It's the gain momentum system. So the only one correct here is this one, 4.8797. So that means now we can rewrite v1f as 4.87 meters per second in this case, because this case, that means since it's positive, that means it's going to the right. So now the velocity of the pendulum after collision is 4.87 meters per second to the right, or you could write as plus. And then to prep for the next problem where we have to find how long it will take for the block to stop, I'm going to find the velocity of the block after collision. So what we declared earlier was v2f is equal to m1 v1i minus m1 v1f all over f2. And now we have all our values. So this is v2f is equal to 1.8 times 7.668 minus 1.8 times what we got here, 4.879. This is all over 0.4, which is m2, and this 4.879. That means the pendulum is moving to the right. And so once you do that, you should get a simplified answer about 12.55 meters per second as the speed of the block when it's moving, or in this case, it will be going, the velocity will be going to the right, or the positive x direction. For 1f, we're trying to find the time it will take to come to a stop. So first we're going to set a net force, which is going to be equal to ma. In this, we're using net force in x direction. So in this case, the x direction is just fk, it's equal to max, and fk is equal to fn times mu. But we're going to try to find our fn, so we're going to set up the net force in the y direction. So net force in y is equal to may. So we have fn minus fg, because those are the only two forces in the vertical direction that are acting on the block. So to small m times AY, which is 0 because it's still on the ground. So now we have Fn is equal to Fg if we move it to the right, because then this is just 0 on this side, which is also equal to Mg. So now we can look over here. So we have Mg mu after we plug in Fn as Mg into Fn is equal to Max. If we cancel out the m's, we have G mu is equal to Ax. I'm going to put a negative to represent that. And in this case, it will be equal to negative 1.568 meters a second squared is our Ax. Now we're going to find the time. So it will be change in time is equal to Vf minus Vi over A. This is the change in velocity. So now we just start plug our numbers in. So Vf in this case, it's 0 because we're trying to go to a stop. Our initial speed after the collision for the block was 12.548 meters per second, which we found earlier. And then for time it will be, and then for acceleration is 1.568, and then negative 1.568. And once you do that, our change in time is just 8.002 seconds. Okay, so for 1g, we're trying to find the angular speed after this, but first we need to find the distance. So we're going to set it up. Common form, vf squared minus vi squared is equal to 2a times d, and then we're set up a over here, so we net force is equal to ma. In this case, it's just the force of friction to ma. And then what we know is that Fk here is just to be mg, because then the only horizontal force will be mg, which is the force of gravity, times mu, because all mg is here is all of the vertical. Fn in this case is due to force of gravity, mu k, so ma. So then it'll be negative g mu k, because we're going against the positive motion. And so now your acceleration will be about negative 1.568 meters a second squared. That's your acceleration. So here you just isolate, so vf squared 0 because it's getting to a stop, so we negative what we found earlier, which was 12.55 squared over 2 times a over 2a, which is negative 1.568. That'll be equal to d, in which case d is going to be equal to about 50.2 meters. We're going to find the vf squared for f. Now this one's going to only 3/4 the distance, so it's vf squared, and now it's time is equal to vi squared plus 2a times, in this case, d times 3/4. So it's vf's, let's see, so I'm gonna square root this after, so it's vi is 7.6, no, it's not 5, it's 12.55, 5 squared plus 2 times negative 1.568, which is our acceleration, times 50.2 times 3/4, and then you could square root it, and then your vf here should equal about 6.273 meters a second. That's going to the right. And then you could just set up MVR. So we set up angular momentum. So in this case, we're going to do MVIR is equal to I total times omega, because then we know now it's going to stick to the block. So then we're going to start plugging in our numbers, so then spinning up I total. So what we know is, first I'm going to plug in m, which is 0.4, our vi is 6.273, and then we're going to r here, it's going to be distance from the pivot, which in this case at the top, so it'll be 2/3 L, so it's L is, in this case, is 5, so it's 5 times 2/3. And now we're going to set up I. So what we know first is the I of the rod from the pivot, which is 1/3 times m of the rod, which in this case is going to be 1.1 times 5 squared, because that's the length of the rod, plus, and we're going to use parallel axis theorem, because now we're treating it as a point mass, so the point mass is 0.4 times, which is the distance away from the pivot, which is 2/3 L, or 2/3 of 5, so 5 times 2/3, and we square that, times that by omega. And now we just isolate it, so it's 0.4 times 6.273 times 10/3 all over, we divide by this I total right here, is 1/3 times 1.1, hold on, let me focus, 1.1 times 5 squared plus 0.4 times 10/3 squared, is equal to omega. In this case, your omega will be equal to about 0.614 rads a second. Okay, so next for 1h, we're going to be trying to find the height. So we're going to set up MEI equal to MEF, which is going to be how it is after it collides with the block collides with the rod. And so we're going to set up KE rod. So in this case, it's 1/2 I total times omega squared. And then we're just, and it's all going to be converted into PE gravity. So that will be set up as M total times G times H, which we're trying to find. And we know I total from our previous question was 0.4 times 10/3 squared plus 1.1 times 5 squared over 3, and then we're going to divide by M total. So M total and G. So we know, so we M total times G is equal to H. And so I'm gonna rewrite M total and G. So let me write this first. So 0.4 times 10/3 squared plus 1 times 5 squared over 3 all over 2G M total, which is 1.1, which is the mass of the rod, plus 0.4, which is the mass of the block after it because it collides and it sticks, to H. And you should get about and once you plug all those into the calculator, you get 0.17 meters as the height from the center, height of the system goes after it collides. Okay, for the last one, for 1I, we're going to be trying to see what happens if it changes where the block strikes. So first, I'm going to write out angular momentum again. So in this case, we're going to start initial. So M here represents the block times V times R, VF, or VI times RR, which is equal to, or actually we're going to rewrite this R as our new one, which is all over 2. And then it's going to be 2I total times omega. So now we had to, so these ones are the same. So it's the mass of the block was 0.4 times the VI, which was 6.273, and then if I were to, and the L is 5, so it's 2.5. And now we have to write a new I total. So if we rewrite this, it will be, so we could keep, first we're going to keep the rods in like natural inertia, just above its pivot, which is 1.1 times, which is its mass, times the length, which is 5 squared. This is all over 1/3. But now what we have is a new, where the block hits. So we could so now it's 0.4 because we're in the parallel axis, but instead of our 5 times 2/3, it will be 5L/2. So it'll be 5/2 squared, and then we still have omega here. And now what we can do is we're going to isolate for this omega. So it'll be 0.4 times 6.273 times 2.5 all over. This is 1.1 times 5 squared over 3 plus 0.4 times 2.5 squared. And this is equal to omega. And now our new omega is 0.537 rads a second. And now if we compare that to the previous one, which was 0.4, this is omega prime. So omega was originally 0.6144 rads per second. So since this is greater than this, that means if we want to lower it to L/2, it decreases. The angular speed decreases.